Proxima Centauri, the nearest star to our planetary group, has for some time been a subject of interest for cosmologists. This little red dwarf, discovered in 1915 by Scottish space expert Robert Innes, is essential for the Alpha Centauri framework, which likewise includes Alpha Centauri A and B. Regardless of its vicinity, just 4.24 light-years away, it remains undetectable to the naked eye due to its relatively low brilliance. Anyway, Proxima Centauri holds tremendous scientific esteem, particularly as the host star of Proxima B, an exoplanet that orbits within the star's habitable zone. Red dwarfs like Proxima Centauri are smaller, cooler, and significantly longer-lived than stars like our Sun. Their low glow makes them challenging to notice, yet it also implies their habitable zones are much closer to the star. For Proxima Centauri, this means an orbital distance of just 0.05 astronomical units, a simple fraction of the distance between Earth and the Sun. This closeness exposes Proxima B to serious stellar activity, including frequent solar flares and high levels of radiation, making its atmosphere distinctly different from Earth's. The discovery of Proxima B was an amazing accomplishment in exoplanet research. Using the radial velocity method, astronomers identified subtle wobbles in Proxima Centauri's position caused by the gravitational pull of an orbiting planet. These wobbles allowed researchers to measure the planet's mass and orbital period. In 2016, the European Southern Observatory formally confirmed the presence of Proxima B, marking a breakthrough in the search for potentially livable worlds beyond our planetary system. While ground-based observations have provided significant insights into Proxima B, they come with huge constraints. Atmospheric distortion and light interference prevent Earth-based telescopes from capturing detailed information about the planet's surface or atmosphere. Most of the data we have, like its mass, distance from the star, and orbital characteristics, depends on indirect measurements. To reveal further insights into Proxima's environment and its potential for life, more advanced observational tools like the James Webb Space Telescope, JWST, are critical. Proxima Centauri's role as a gateway to understanding exoplanetary systems can't be exaggerated. As the nearest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima B, in particular, represents an enticing chance, a rocky, Earth-sized planet with the potential to harbor water and perhaps life. However, the challenges posed by its harsh climate make it a complex puzzle for researchers to solve. The James Webb Space Telescope, JWST, is not just another tool in the arsenal of astronomy. It is a revolution. Designed to succeed the Hubble Space Telescope, JWST was conceived to address the limits of its predecessor and push the boundaries of human knowledge. While Hubble has provided significant insights into the universe, its capabilities are limited by its focus on visible and ultraviolet light. JWST, conversely, is built to observe the universe in infrared frequencies, allowing it to look through vast dust clouds and uncover phenomena invisible to Hubble. One of the key design features of JWST is its primary mirror, which spans an impressive 6.5 meters in diameter, over twice the size of Hubble's mirror. This larger mirror enables JWST to gather much more light, making it capable of observing incredibly faint and distant objects. Covered with a thin layer of gold to enhance its infrared reflectivity, the mirror is composed of 18 hexagonal segments that work together to form a highly sensitive observational platform. Another groundbreaking development is JWST's sunshield, which keeps the telescope's instruments at a constant temperature of about -233 degrees Celsius. This ultra-cold environment is crucial for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point, L2, a stable position around 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. The telescope can study everything from the earliest galaxies to the atmospheres of exoplanets like Proxima B. Its ability to detect infrared light is especially important, as it allows astronomers to focus on redshifted phenomena, objects whose light has been stretched to longer wavelengths as the universe expands. JWST's capabilities extend far beyond simple observation. It is designed to answer some of the most fundamental questions in science, including the origins of galaxies, the formation of stars, and the conditions that could support life on other planets. With its state-of-the-art instruments, including the near-infrared camera NIRCam, the mid-infrared instrument MIRI, and the near-infrared spectrograph NIRSpec, JWST is not just a telescope. It is a time machine, a laboratory, and a testament to human ingenuity. Proxima B has captivated scientists and the public alike as a potential second Earth. Situated within its star's habitable zone, the planet has the right conditions to potentially support liquid water, a key element for life as we know it. With a mass roughly 1.17 times that of Earth, Proxima B is likely a rocky planet similar in composition to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima B is far from an ideal twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual sunlight while the other is in eternal darkness. This creates a unique environment with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, may offer a narrow, peculiar zone with conditions mild enough to support life. The challenges posed by Proxima B's climate are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can emit bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima B retains any atmosphere, it would likely require a strong magnetic field to protect it from radiation. Without such protection, the surface and atmosphere would be hostile to life as we know it. Despite these challenges, scientists remain hopeful about the potential for life on Proxima B. The planet's location within the habitable zone suggests that liquid water could exist, either on its surface or in subsurface reservoirs. Life may adapt to the harsh conditions. Much like extremophiles on Earth, organisms that thrive in extreme environments such as deep-sea hydrothermal vents or high radiation zones. These adaptations could include radiation resistance, subsurface habitats, or unique biochemical processes. The search for life on Proxima B is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions. Are we alone in the universe? Proxima B presents an enticing possibility, a rocky, Earth-like world that could harbor the conditions necessary for life. As our technology advances, so too does our ability to explore this fascinating planet and uncover its secrets. While Proxima presents tempting possibilities, its environment is profoundly influenced by the nature of its host star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf, smaller, cooler, and significantly less luminous. Its reduced size and temperature mean that its habitable zone is much closer, pulling Proxima B into an orbit just 0.05 astronomical units from the star, about 4 times closer than Earth is to the Sun. This proximity creates a unique set of challenges for the planet and any potential life it may harbor. One significant issue is Proxima Centauri's stellar activity, particularly its intense and frequent solar flares. These flares are sudden, powerful bursts of energy that release high doses of X-rays and ultraviolet radiation. Such events are much more common and vigorous in red dwarfs than in stars like our Sun. For Proxima B, this means a constant barrage of high-energy particles, which could strip away the planet's atmosphere over time. Without a protective magnetic field, any atmosphere on Proxima B would be vulnerable to erosion, exposing its surface to harsh radiation. Even if Proxima B retains some of its atmosphere, the radiation from Proxima Centauri presents serious challenges for life. High levels of ultraviolet radiation can break molecular bonds, preventing the formation of complex organic compounds. This would severely limit the potential for life to develop or sustain itself on the planet's surface. On Earth, organisms like Deinococcus radiodurans have evolved mechanisms to repair DNA damage caused by radiation, suggesting that life on Proxima B could similarly adapt. However, the degree of radiation resistance required would be extreme, potentially necessitating entirely new biochemistries. Interestingly, Proxima B's tidally locked nature may offer some protection. While 1/2 of the planet faces constant radiation from Proxima Centauri, the planet's dark side could act as a refuge. Surface regions or deep caves could shield potential life forms from the worst of the radiation. Additionally, if Proxima B has subsurface oceans, they could provide a stable, radiation-free environment where microbial life might thrive, much like the ecosystems around hydrothermal vents on Earth. Despite these challenges, scientists remain optimistic that Proxima B's unique environment offers a valuable opportunity to study the resilience of life. By understanding how organisms might survive or even thrive under such conditions, researchers can expand their knowledge of what makes a planet habitable. Proxima is not just a potential home for life. It is a cosmic laboratory for testing the limits of life itself. The planet's proximity to Earth and its position within the habitable zone of its star make it an ideal candidate for further study. With new telescopes and instruments, researchers will continue to monitor Proxima B for signs of habitability and life. Whether Proxima B can support life in the traditional sense remains uncertain, but its discovery marks an important step in the quest to answer one of humanity's greatest questions. Are we alone in the universe? The discovery of Proxima B and its potential habitability is just one piece of the broader puzzle of exoplanet research. The next steps in this field involve not only refining our understanding of planets like Proxima B, but also expanding the search to other star systems. Thousands of exoplanets have already been discovered, with many residing in the habitable zones of their parent stars. The James Webb Space Telescope, JWST, is expected to revolutionize our ability to analyze these planets, particularly their atmospheres, in unprecedented detail. JWST's spectroscopic instruments can detect the chemical composition of an exoplanet's atmosphere, identifying molecules such as water vapor, carbon dioxide, and methane, key indicators of potential habitability or biological activity. Observing the atmospheric composition of exoplanets, especially those in their star's habitable zones, will allow scientists to detect signatures of life, or at least determine the conditions for its possibility. While Proxima B has garnered significant attention due to its proximity and promising conditions, other exoplanets orbiting stars similar to our Sun, such as those in the Alpha Centauri system or those discovered by missions like TESS, Transiting Exoplanet Survey Satellite, are also prime candidates for future exploration. The more we discover, the clearer it becomes that the universe is brimming with potential worlds where life could emerge. Whether it be within the habitable zones of red dwarfs or larger stars, the key challenge is deciphering the complex interplay of factors that make a planet suitable for life. This quest is further fueled by the growing technological advancements in space exploration. Future space missions, including those aimed at studying exoplanetary atmospheres and planetary surfaces more directly, may take inspiration from current endeavors, like the successful landing of rovers on Mars and the upcoming missions to ice moons in our own solar system. These missions will not only help us understand the Earth-like environments beyond our solar system, but also provide insights into the broader question of life's resilience in extreme environments. Ultimately, the search for life beyond Earth and the study of planets like Proxima behold profound implications for humanity's place in the cosmos. While Proxima B may not be the next Earth, its discovery highlights that habitable worlds are not confined to our home planet. It also underscores the importance of continued exploration and technological innovation to answer some of the most fundamental questions about life, the universe, and everything in between. As we expand our reach into the cosmos, the coming decades promise exciting discoveries and potential breakthroughs. Whether we find microbial life on Proxima B or uncover more Earth-like planets across the galaxy, each finding will shape our understanding of the universe and our place within it. The exploration of distant stars and their planets, once limited to the realm of science fiction, is rapidly becoming one of humanity's most thrilling and inspiring scientific pursuits.